Hello everyone, welcome to this video. In this video, we are going to solve this question which states that if G be a finite abelian group, so that means the number of elements here is finite and all the elements commute with each other, A and B, if they are two elements taken from this group G, we have to prove that this set which is generated by AB, which is of this form, which has A raised to some integer power, B raised to some integer power, they are multiplied together. Correct. So now we have to show that all the elements collected together, they form the subgroup of G. Correct. This is the first question. And in the second part, we have to tell what is the order of this subgroup, and can we tell the order in terms of the order of A and in terms of order of B. Let's have a look at these two questions here. So first of all, let's have a look at proving this subset to be a subgroup of G. So in order to prove this subset to be a subgroup of G, we can either make use of one-step subgroup test or two-step subgroup test. For that, if we consider two elements A and B from G, correct, such that the order of A, we consider it to be N, we consider the order of B to be M. So what does it mean? It means that when you take A raised to power N, that would be E, and when you take B raised to power M, that would be the identity element, correct? And no integer less than N or less than M would give you identity, correct? Okay, now we have assumed this thing. Now in order to prove this to be subgroup, we first of all show it is non-empty. We say it is non-empty. Why? Because it surely contains the identity element within it. Why? Because you can write identity element as E into E, correct? Now because A raised to power N is the E, you can write first E as A raised to power N and the second E as B raised to power M. So you have written E in this form, A raised to power N, B raised to power M, which is in this form. Hence, it is a member of this subset generated by AB, correct? So therefore, it at least contains the identity element within it. Therefore, it is non-empty, correct? This proves our first point. Now, let's prove our second point, where we take any two elements X and Y from this subset and we prove that X, Y inverse also belongs to this subset, correct? Now because X and Y both are taken from the subgroup generated by AB, so both could be written as powers of A and B, where these powers are integers, correct? So we assume X to be A raised to power I, B raised to power J, and Y as A raised to power K, B raised to power L, correct? So now we consider this term XY inverse, and let's solve and see what do we obtain from here. We can substitute the value of X, the value of Y, and then simplify the powers using the laws of exponents. You have A raised to power I minus K and B raised to power J minus L. Now this thing is a member of the subgroup generated by AB. Why? Because both I minus K and J minus L both are integers. Why? Because individually I, J, K, L, they were integers, and under addition and subtraction this set is closed, correct? The set of integers is closed, hence we can utilize this term here. Therefore by one step subgroup test, this subgroup generated by AB is a subgroup of G, correct? So this proves our first part. Now for the second part, we have to say about the order of the subgroup AB, correct? Generated by AB. So this subset would contain as many elements, we would count the number of elements present within this subgroup. So let's do that, but we do not exactly know what are the elements, but what we know is the elements would be of such kind, right? So how many such A raised to power element would excuse me, would be present here, and how many B raised to power elements are present here? Now because you know the order of A is N, so you can go up to N. So because A raised to power N is identity, so you can start from A raised to power 1, A raised to power 2, in fact A raised to power 3 and so on up to A raised to power N, where what is A raised to power N? A raised to power N is identity element, and if you further calculate N plus 1, it would be equal to A raised to power 1 and so on. So that means the elements would start repeating themselves after N. Similarly for the power B, because you know the order of b is m, so that means we can maximum go up to b raised to power m, which is identity, because thereafter if you calculate it would just be equal to b and the elements would start repeating themselves, correct? So that means how many choices for a are there with us? There are in total n choices with us. And how many choices for b are there? In total we have m choices for them, correct? And we do not, here the order does not matter. Why? Because our group G is given to be an abelian group, correct? So therefore the order does not matter. If the order does not matter, so we only have these many combination of elements. You can fix b raised to power 1 here and take all the combinations of a raised to power 1, a raised to power 2 up to a raised to power n. Similarly, for you can keep b square as fixed and take different powers of a raised to power 1, a raised to power 2 up to a raised to power n. You can keep going on like this. So how many such elements are there? There are total n elements. These are also total n elements. These are also total n elements. These are also total n elements. So how many such pairs are there? We are taking b raised to power 1, b raised to power 2, b raised to power 3 up to b raised to power m. So in total we are having m such combinations. So therefore the order of the subgroup generated by a and b would be n into m, and you know what is n? N is the order of a. What is m? M is the order of b, correct? So I think this solution is the correct answer for this. If you do not think it to be the correct answer, or if there is some mistake in this part, you can let me know in the comment section. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.